Welcome to the next video in the Discrete Math video series, and in this we are answering the exercise that we left off last time. So here are the solutions. And so the first one is Adam does not have an iPod. Now you could, try to sort of just do a very literal, say that the negation of this is not Adam has an iPad or iPod. And in some way that's not technically wrong, but it is not the most natural English. So this, somewhat the goal here is to identify how English sort of translates into and out of logic, kind of, or symbolic abstraction. And so you want to be able to recognize, how you write, like, what is the correspondence, between this and our sort of logical formalism. And it's just worth sort of understanding that even though the word not occurs in the middle of the sentence, when we get around to formalizing it with formal logic, we'll put, just to have a system, we're going to put the negation on the outside of the sentence. And, maybe another way to kind of get at, what the point here is that, when you negate this in English, you put the not here, and then the word does appears. And that has to mean that English is a very weird language. And, like no other language that I know of does that kind of thing. And so, the study of logic should not be language dependent, right? It's not the study of English, it's the study of logic, which should be shared at some kind of more primitive human or cognitive level. And so in any case, but it's also worth making sure that you understand, like, how our particular language of English sort of translates in and out of this much more formal and broader thing. So anyway, that's the point of what we're trying to get at here. And so this is the most natural English formulation of the negation. Okay, there is at least one pickle in Poland. Again, right, you don't just put a not at the front of the sentence. Instead, you would say something more like there are no pickles in Poland. That is a pretty natural translation of the, sort of like negation of that sentence. Okay, and then finally, this is an equation, and although this might not be really an English rule so much, maybe it's more of like a natural mathy rule, but that, again, right, we want to kind of give the natural translation of the negation of this sentence, and the natural mathy translation is to put a line through the negation to indicate that we are negating the assertion of this equality. Okay, let's move on to new topics. So we can use a table like the following to display how negation changes the truth values of a proposition. So for now, this might seem tedious and unnecessary, but a tabular method will prove very helpful as propositions become increasingly complex, which they will. So here's my favorite way to write a truth table. It's not the same as the textbook's way. There are some similarities, but there are also some divergences. So what we share, me and the textbook, both like to do a truth table by making the very first column the propositional variable that occurs in the proposition, and then listing all of its possible truth values. In this case, it could be true or it could be false. So that's the true row. This is the false row. Next, I write the proposition that we are forming a truth table for. The book does that as well, although especially when we get to more complicated propositions, you'll see how the book's truth table and my truth table look increasingly different. I like my way because it involves less repetitive writing, but it is a matter of taste. They are equivalent, and if anybody requests, I may do a truth table or two the way that the book does, if anybody requests it, just in case you need to follow it that way or whatever. But in any case, so I put the proposition here, but unlike the book, I put each symbol in its own column. And then from there, here's what I do. I like to transcribe, right? Take all the values under P here. And by the way, just note, there's a hard separation, right? Like the stuff to the left is kind of different from the stuff to the right. So there's a hard separation here. And so the first thing that I do is I transcribe everything under the variable P over to wherever I see P here. So if it occurred in many places, as it will later on, I would do this transcription in many places. But I do this transcription of the truth values that are underneath the variable. Okay, that's step one. Step two is to look for the next symbol. In this case, the next symbol would be the negation, the only other symbol here, and then apply the truth operations for it. So, negation will take this true value and turn it false. So therefore, I get a false value here, right? Applying negation to that true, I get false. And that goes under the negation symbol. I apply negation to that false and I get true. And now the table is complete. You'll see this become a bit more interesting as the propositions get more complicated. That's how I make that truth table. Okay, let's move on to further topics. So not only do we have negation, but we also have conjunction. Notice that negation only applies to a single proposition at a time, whereas conjunction forms a new proposition out of some two propositions. And this is meant to be a representation of a sentence that has the form P and Q, right? So if you assert that P is true and you assert that Q is true, that's the conjunction, and we represent it this way with this little upward wedge symbol. There is also disjunction, meant to represent P or Q, and it's written with a downward wedge. And then there's XOR. So, by the way, this disjunction with the downward wedge is called the inclusive disjunction. And it's inclusive because, we use this symbol to represent when P or Q or both could be true, right? So let's say that you could get to my house by taking I-95, or you could take State Road 20 or something like that, right? Two different paths. Well, that would actually, that's a much better example for the exclusive OR, right? Because you could take it, right? You could get to my house by I-95, or you could get to my house by State Road 20 or something, but you couldn't do it by both, right? So you'd probably express that one with an XOR. That's the exclusive OR. It says that one or the other is true, but not both. So then what would be an instance of an inclusive OR? I guess maybe somebody is passing around cookies, and the cookies are chocolate chip or peanut butter, and they say you can have either. You could have chocolate chip or peanut butter, and hopefully they mean that you could also have both if you wanted. So that would be an inclusive OR, right? One is true, you can have chocolate chip, or the other is true, you can have peanut butter, or you could have both, right? Both, right? Is acceptable, right? Results in true, let's say. So that's disjunction. There's the inclusive disjunction written this way, and there's the exclusive disjunction written that way. Let's talk a little more precisely about exactly how these things operate on truth values. So conjunction is true when both of them are simultaneously true, right? So if you have true and true, right? P is true, Q is true, then the conjunction is true. In any other case, the conjunction is false, right? If P is false, then the conjunction is false. If Q is false, the conjunction is false. If they are both false, then the conjunction is false, right? Because this is supposed to represent, like you are asserting P, and also, you are asserting Q, so just one of them being false is enough for your conjunction to come out false. So, okay. Then there's disjunction, and it's kind of a dual rule, right? It's, if both of them are false, then the whole thing comes out false. But if just one of them is true, or if both of them are true, it comes out true. And that's the inclusive disjunction, right? But you just need one of them, right? It's one or the other. So at least one needs to be true for the whole thing to come out equal to true. If both are false, then it is false. Okay. XOR will come out false if the two sentences have the same truth value, right? And that, if you think about what we said about XOR, that it's kind of like an exclusive or it is an exclusive OR. Well, if they have the same truth value because they are both false, we know that just like up above, that results in a false, right? There's no difference there when they're both false. But also when they're both true, the sentence results in false. So in general, whenever they have the same truth value, the sentence results in false. But so long as they have different truth values, right? One is true and the other one is false, in that case, the XOR between P and Q comes out true. Okay, let's see all of this reiterated in their truth tables. So here are truth tables. And notice this time that we now need 4 rows for the truth table. So we've got P could be true and Q could be true, right? That's where they're both true at the same time. You could have that P is true, Q is false. Distinct from that is P false, Q true, and then false, false. So when you have 2 propositional variables in the same proposition, then you need 4 rows for your truth table to capture all possible ways that P and Q could be either true or false. Okay, with that set up, we now go and look at the truth values for any of these sentences. And again, my favorite way to do this, and notice, by the way, that this is the conjunction table, this is the disjunction table, and this is the XOR table. And so I like to copy over all of my truth values row by row wherever I see P. So I just do a transcription of all those truth values that you see here. Okay, do it again. True, true, false, false, true, true, false, false. That's a pure transcription of the values under P. Okay, let's do it for the values under Q. So true, right, because there's a true there. False, because there's a false there. True, false. Okay, so there's the transcription for Q, and we do it again everywhere that we see Q. Okay, now that the transcription is done, we let the operation operate on the truth values that are to its left and right. So when you've got true and true, the result is true, right? True conjunction true is true. When you've got true and false, the result is false. When you've got false and true, you've got the result is false, and false results in false. So that's how you compute the truth table for conjunction. If we want, I do this little mark on the page to indicate that I'm putting those two together. It's a little provocatively similar in shape to the and symbol itself. That's a little bit of an accident, although it's a happy accident, I guess. Well, let's reproduce it. Let's put together the true and true using disjunction, and let's again kind of use a sort of notation that's a happy accident in that it's similar to the disjunction symbol itself. Anyway, so true or true results in true. True or false results in true. False or true results in true, and false or false, well, that one is the special case where if they're both false, then the disjunction comes out false. Okay. My notation system might be stretched to its max, because how could I possibly do an O plus here, indicating that these two values on either side are getting put together? Well, in any case, the truth values match, and therefore on this row, the XOR comes out false. In this row, the truth values match, and therefore the XOR comes out false. In these two rows, the XOR is the two values mismatch, therefore the XOR is true in those rows. And so there's the truth table for these symbols. Again, just like last time, just like we saw with negation, if we wanted to have if we wanted to kind of operate directly on the truth values, we could say that true conjunction true results in true, and that would kind of tell you the same thing as what the table told you right here, right? That is the same thing as P being true, that's the left side being true, Q being true, that's this true value, and then seeing that the result right here is true. So this portion of the truth table tells you the same thing as what this little equation down here would, and likewise, this right here tells you the same thing as this right. Okay. Let's carry on. So finally, an exercise, right? It's been a while. So let's now do an exercise in taking English sentences and abstracting them into symbolic expressions. So this time I don't want to stick to English. I want to take the English and turn it into an abstract symbolic logic expression. So this is the sentence, the deer come through here during the winter, but not. How do you represent but not? We know how to do we know how to do not. That maybe is not the hard part here. But the word but, we've seen and, we've seen or, we've even seen two different versions of or. But how do you do the word but? What is that in our logical symbols? Well, that's the challenge. Maybe think about it. Maybe it's an unfair exercise since I haven't told you how that goes, but think about it. At least make a guess. But anyway, and then there's like some other sentence here, right? Like, but not during the summer. Okay, well, whatever. So you can call this anything you want. You could call it P, you could call this Q. That part is not the most interesting. The interesting part of this challenge is how do you symbolize but not logically when you have these two propositions? Okay, that's the challenge there. Similarly, it is not time to leave, but we can start getting ready. Either the avocado is unripe or rotten or both. Man, aren't avocados finicky but delicious. Either the apple is unripe or ripe or rotten, but it cannot be any two at the same time. This one is definitely a sort of extra challenge problem. And part of the point of this one is to realize, and it's going to be a little tough to do it, so you want to maybe think about it especially hard. The XOR may not work as nicely as you hope it does for problem number 4. So anyway, there's your challenge, and in the next video, I'll show my solutions.